let's start. So it's my great pleasure to introduce Sebastian Torres. So he will talk about this window.
Okay, thank you. So yeah, if you have any questions, just let me know. Maybe you can yell very loud or give us a call, or if you're here, just raise your hands. But, so what I'm gonna do is, so this is good enough. Talk a bit about derived categories and how windows play into derived category. So I'm gonna be interested in, let's say that X is an algebraic. Let me take this one. Let's say that X is an algebraic variety. So then I'm interested in dBx, the derived category of X, which, like roughly speaking, we've talked about this, but you can think of this as basically chain complexes of coherent sheaves, bounded. With the extra thing that quasi-isomorphisms are isomorphisms. Quasi-isomorphisms are now invertible. And by the way, everything I'm gonna say, you can think of it over C. So let's say that this is a complex variety. Let's not worry about other fields. So yeah, the idea is that the derived category should tell you something about the geometry. There's like an ongoing effort of trying to find some, birational invariants to the derived category. Griffith's components are not quite well defined, but in some cases you can do something. And for example, if your variety happens to be final, for instance, the derived category recovers you the variety itself. There's no other variety that would have the same derived category. So there's many reasons to be interested in studying this and studying decompositions, like semi-orthogonal decompositions of this. And one thing I could try to do is see, for example, what happens if you take X and then you replace X by something that's birational to X. What would happen to the derived category? So there are some known results about this. The most classical one would be the following. So so what happens under birational maps? So the easiest birational map that you can think of is just a blow up. So for example, if you take a blow up, there's a classic formula by Orlov that says that if you say, let's say that you have X and you blow up, let's say this is all smooth. So you blow up a smooth variety of some codimension, and it has, so this is the blow up along Y, and there is some exceptional divisor. So if you do that, then how does the what happens to the derived category of X tilde? So then there's this theorem that says that the derived category of the entire X tilde, well, it will contain the derived category of X just by the pullback. The pullback is a full faithful embedding, but also it will contain a bunch of copies of the derived category of Y. So that's like a classical result. Yeah, so and this is like C-1 copies where C is the codimension. And the way you achieve this embedding of dBy into this derived categories by these functors that are from. So there are these embeddings that are given by. So the way you have an object here and you embed it and you see it here is you pull it back first. So let's say this is pi. You pull it back. And then you tensor with what would be called like that Fourier kernel, which is like O of E, twisted by some multiple of E. And then and then just if this is the inclusion, then just push forward. These are the functions, and if you go all the way from 1 to C minus 1, you get all these copies, and this actually constitutes a semi-orthogonal decomposition. Meaning basically that this entire category is generated by all these blocks, and also semi-orthogonal in the sense that there's no map from one block on the right to one block on the left. Yeah, so that's the easiest irrational map that you can think of. But if you want to extend this to, for example, flips or flops, there's also something you can say. So what happens if you take, let's say, a standard flip? So this what happens with blow-ups. How about a standard flip or a flop? So what is that? Flip would be basically when you take a variety. Let's say that inside your variety there's some copy of pk. You blow it up, and then let's say that you blow it up in a way that the exceptional divisor. So let's say this is x tilde. So let's say that the exceptional divisor is some pk times pl, and then you blow it up and then you blow it down. So then the exceptional divisor in either way. I mean, what this you can contract either to pk or to pl. So if you have that situation, that would be a standard flip. So whenever you have this picture, that's a standard flip, and that's like again like another possibility for a kind of standard birational transformation. Of course, these two are birational to each other, you know, by means of this these two maps. So these two are supposed to be just blow downs. So whenever you have that, well, so what happens is that so that the canonical bundle on will flip from positive to negative depending on the signs of who's bigger, like K or L. So basically, like for example, like if you do the canonical bundle of X, and you restrict it to pk, that would be like O of L minus K. And if you do the canonical here and you restrict it to this one, it would be K minus L. So that's what you do. For example, if you're doing like the minimal model program and you want the canonical bundle to become, you know, positive on some curves, or yeah, you try to flip some loci and stuff like that. So if L is equal to K, this would be a flop. And so well, the theorem is the following. So if K is bigger than L, meaning that the canonical goes from being negative to being positive on this locus, on these loci, then there is an embedding of d b x, you know, the derived category of this guy embeds in the derived category of this. So again, we have, well, I mean, I guess I'm about to erase it, but again, we have like a way of embedding one derived category into another when they are related by some particular birational transformation. And in the case, this is a flop. So if they are equal, then this is an isomorphism, an equivalence of categories. Yeah. So in fact, this is you know, for a standard flip, it would look like this. But more generally, there's a conjecture that has not been proven that says the following. This we don't know yet, as far as I know, is that if you have a generalized flip or flop, so if we have a generalized flip or flop, which means something like this, like a picture where you have like a common resolution of x and x prime. I mean, they let's say both are smooth, for instance, but like a common blow-ups in this fashion with actually like pi, and not blow-ups, but just birational morphisms from x tilde to x and x tilde to x prime, so that these two are birational to each other. And let's say that that if you take the pullback of a canonical, that if you subtract the pullbacks of the canonicals, so let's say that that these two, that this difference is effective or equal to 0, then we should have also an embedding of in the derived categories. And there should be an embedding of this one into this one. So again, like every time you do a flip, you expect that one of the derived categories would be smaller, but it's not known in general. If it's a flop, this is a flop case, then it is expected to be an equivalence of categories. And by a theorem of Bridgeland, this actually is true in dimension 3, but beyond that, I don't know. I mean, I think we don't know. I don't know if there are many. There are other results. Yeah. So I want to focus on some particular cases when you have, you know, again, two varieties. They are related by some birational transformation between them, and you can think of these many times like there's something in the middle that's you know, that's mapping to both of these, and like if you're in the middle, you have two choices. You can go one way or the other, right? And this is what we would call like a wall, and then and either side of the wall there is one or another option. And one way to achieve this kind of picture is by geometric invariant theory. This happens a lot when you do GAT quotients. So let's focus on that particular kind of flips and flops, and in that case, we'll be able to say a lot, and that's where the windows will come in. So So let's say first of all, like what's the GAT quotient? Very briefly. So what is the GAT quotient? And then from variation of GAT quotient, this kind of picture will show up, this wall crossing picture. So yeah, what's the GAT quotient? So when you want to define, let's say that X is a variety, and then you have a group. Let's say that this is smooth. You have a group that is reductive. So you want to define a quotient. No. You want to define the quotient of X mod G. So there's like several approaches to do such thing. And the approach of geometric invariant theory is say, okay, like in the quotient, the sort of like the coordinate ring of the quotient should be the coordinate ring of X, but only the ones that are fixed by G. So G will act in the coordinate ring of X. And if you only consider the invariance in that ring, that should be the ring of the quotient. So that's the idea. And the formal way to state that is that, so the GAT quotient, and I'm going to write it like this. So it's as follows. So the coordinate ring will be you take it's going to be a product of sum of the global sections of powers of an ample line bundle, and then you have to consider only the invariance. So if this were not if you don't take the invariance, it would be this would give you exactly X. And you take the invariance, that gives you the quotient. So this is where L is an ample line bundle. And G acts on L, or you could say G acts on, let's say, like the total space. If you see the bundle as a variety itself, it acts on L. So you would say like A is a G linearized ample line bundle. Here there's something that's not quite true, because I said the GAT quotient. Of course, that doesn't make sense if you think about it, because there's no one GAT quotient. It's like a GAT quotient, because this construction depends heavily on how I choose my ample line bundle in the first place. And even if I already chose my ample line bundle, I need to choose how G would act. This is an extension of the action on X, but in general there's no unique extension to the action on L. There can be many of those. So the fair way to write this would be, let's say that this is the GAT quotient. I'm going to write like a subscript L, saying that this is the GAT quotient that you would achieve when you use this G linearized line bundle, and I mean L with a particular action, right? Because different actions give different L's, or different actions give you different GAT quotients. And well, the GAT quotient is doesn't carry like an honest quotient map as you would expect from the entire X, but almost, because when you have this X and this quotient, there's no map like this, but there's a rational map. There's like a rational quotient map, and it's only defined on whatever points you can send to this, which is basically points where at least one of these is not zero, because it's a project, so not all of the coordinates can be zero. So that's what we call the semi-stable locus. So from the semi-stable locus, then you do have a map like that. And the semi-stable locus, let's put it this way, although it's not exactly that, but it's like the locus where this map is defined. I mean, the map could be defined like a little in a slightly bigger set, but let's say that that's like where it's naturally defined. And as I said, like different L's will give you different quotients. In fact, different L's will give you already different semi-stable locus, semi-stable loci. And if you change your linearization or your ample line bundle here, that will give you different stability conditions, meaning different conditions to be semi-stable with respect to one line bundle and with respect to another line bundle. So the way one DAT quotient changes to another was studied by Dolgachev and Hu in their study of variation of DAT. They give it like a very concrete, very complete description of what happens when you vary L. This was done by Dolgachev and Hu. And what they show is that, and this is what we will, assume from now on, this is what we will use to understand how GAT varies from one linearization to another. Well, they call, so they define what would be the G ample cone, which would be basically like the set of all possible L's that you can fit. So this would be like a subcone of the entire Néron-Severi cone of X, but you put like an upper script G here, meaning that not invariance, but equivariant, meaning the different. By this I mean all the possible line bundles with all possible actions of the group G. Well, tensored with R, and this is spanned by all. This is the cone spanned by all line bundles. Let's say ample line bundles. For which, well, I don't need to say ample because, yeah, okay. So we'll show it for which you can do a DAT quotient, and it will, and that amounts to saying that there is at least some non-empty, semi-stable lock. So this would be non-true. This is not empty. So this G ample cone, the set is all possible linearizations, meaning all possible DAT quotients you could have, that can be split into a system of walls and chambers. So this is this has a system. So the theorem is the GM cone has maybe I'll put it here. So the theorem is that the GM cone has walls and it has chambers. So what are walls? Walls are consist of all these line bundles where whenever you take the semi-stable locus and you compare it to the stable locus, meaning those where the orbits are also closed and of the correct dimension, they are not the same. And then the chambers are those where these two things are the same. And whatever that means, I guess the easiest way to say this is that chambers is the set of line bundles that would have given you a geometric quotient. So this is chambers are where the quotient map from the semi-stable locus to the GAT quotient is geometric. So it really like separates orbits. So the picture is well, okay, actually, like part of the theorem is also saying that that you have like finitely many of these, which is not trivial, but also I guess within each wall and within each chamber you have like so within each we get we get the same what's it called, like equivalence classes. We get equivalence classes, meaning like GAT equivalence classes, meaning like a bunch of line bundles that would have given you the same quotient. So the picture is sort of like this. Like let's say that you look at a section of the GM cone, it will have a system of some maybe walls and chambers like this. So, for example, if you choose L to be here in a chamber, so these are the chambers and these are the walls. If you choose L to be in a chamber, and let's say L prime to be in the same chamber, then the two would have given you the same semi-stable locus, the same stable locus, the same quotient. And if you're on a wall, then that if you choose someone here, then the quotient will be not geometric, and then you can wonder what happens on either side of a wall. So, and that's exactly the picture that I'm intending to address now, which is what would happen, what picture we have when you have a wall, and on one side of the wall you have one chamber, and another side of the wall you have another chamber. So you have two different quotients. And there's more to this theorem that I haven't written here, which says the following. It says that in fact all the possible GAT quotients are birational to each other, and every time you have a wall, if we have a wall and let's say in two chambers and two like adjacent chambers, like one on either side of the wall, So let's say that the wall is F and the chambers are like C plus, C minus. So let's say that this is a wall. Here's F, here is C plus, C minus. Whatever linearization I choose here gives me the same. Whatever linearization I choose here, it gives me the same. And those would give me quotients X. I'm going to write it like this. And like this. So those two are actually related to each other via the quotient of the wall. So if you do this quotient, actually both of these map to this one, and these two maps are birational, so that already gives you like a birational transformation between these two. So not only are they birational, but this is like a quite explicit way to say like what the birational map is. So this and the inverse of that, that's the birational transformation that relates to adjacent chambers. Yeah, let me do a couple of examples of GAT quotients. I guess the easiest one would be Pn, you know, like so let's say example, if you have you know the affine space with and you multiply by constants, let's say non-zero constants, then then you can write a GAT quotient. If you choose like an interesting linearization, then you would get a quotient Pn. Here I should say like which linearization I choose, but I mean you either get something interesting or you don't. So there's not much point here in the variation of GAT, but the point here is that in order to get Pn, you don't really have a map from an plus 1 to Pn, but you do have a map from an plus 1 minus 0 to Pn. That's your semi-stable one. Yeah, I should write it like this is my semi-stable. And yeah, and that's all the semi-stable lockers can be in this situation, unless you choose a linearization that gives you that everything is unstable, but that's like not interesting. But or you can also choose like map everything to a point, but that's also pointless. But more interesting would be the following example. So this is example 1. About example 2, if you say, let's say that you have P1 and you have a bunch of copies of P1, and on each P1, let's well, you have the action of PGL2, right? So let PGL2 act diagonally on P1. So then what would be a quotient of this by that? You need to choose a linearization. So you need to choose an ample line bundle with a linearization, which in this case, it amounts to choosing just an ample line bundle, because in this case, there's only one way to extend the action to a given ample line bundle. So a GAT quotient would depend on how you choose your ample line bundle. So you choose an ample line bundle here, which has to be all of Q1 to the n, and that way you get a quotient. PGL2. Yeah. So so what would this parameterize? This is parameterizing what's a point in P1 to the n. You can think of that as n points in P1. So something like, let's say like n points in P1 to the n. You can think of this as P1 and then Z1. It's like n, let's say n marked points in P1. That's what a point here would be. And then if you do modulo PGL2, that's telling you that you're considering this up to projective equivalence. If you move this by a linear transformation, then the next configuration will be the same. Yeah, in the quotient. And the stability condition or the line bundle that you choose to get your quotient tells you what the stability condition will be, meaning which points I will allow in this quotient, or which points are going to be considered to be stable for this quotient. And for example, if L is like O of 1, 1, 1, 1, then it turns out that the stability condition is the following. It boils down to saying that the points that are going to be considered stable, so x is P1 to the n, so the points that are going to be considered stable, well, it consists of tuples again, so tuples. But there's a condition that maybe some of them can coincide. Maybe you could have like, this is a fat one that's Z1 and Z2 are the same. But if you have chosen this linearization, then no more than half of the points can coincide. That's what it's telling you. Such that no more than half. In fact, so let's say that n is 5, and you consider P1 to the 5 modulo PGL2, having chosen this linearization. This parameterizes tuples of points, of 5 points in P1, Z1, Z5, where maybe 2 of them are the same, but not 3 of them are the same. Where no more than 2. And of course, since this is a quotient, it parameterizes this up to projective equivalence. In fact, this is exactly the moduli space M05, which is P1 with 5 marked points. So a rational curve with 5 marked points. That's so yeah, P1 with 5 marked points where only two of them can coincide, not 3 of them can collide together. That's exactly like M05. So in general, P1, like this kind of quotient is some sort of moduli space in some fashion. And in fact, if you do P1 to the 5, you get exactly M05. But in general, it's like a naive, and like in general, P1 to the n P1 to the n modulo PGL2. And if you choose this linearization, this is some sort of like a naive moduli space of this kind of thing. And in fact, if you want to get like M0 n bar, then you have to blow up a few things because you want to consider more stuff. It's like the coarsest moduli space you can think of for P1 with n marked points. If you want to get the actual one, you have to blow up a bunch of stuff. Yes, this one's smooth. Not, I mean, this may even be smooth for. Well, I mean, simple across the device. I mean, for example, if n is odd, this is always smooth. But even then, it's not like the actual moduli space you want to think of. But not only this one is smooth, but for n equal to 5, you don't need to blow up anything else. This is already the moduli space, literally M05 bar. So this is like a series of blow-ups. And of course, this is birational. Okay, so back to the picture. I wanted to tell you about. Again, in general, every time you have a variation of GAT, you have walls, you have chambers on either side of the wall. You have, let's say, 2 chambers, and then if you have like one quotient and then the other quotient, they both map to the quotient on the wall. Let's say that this is the wall, and these are birational to each other. So we want to see what happens now with the derived categories, because that's what was the starting point. Like that was what I wanted to study. Like what happens for these 2 derived categories. Maybe one of them is embedded in the other, maybe partially. So and this is where the windows come in, and this is like a series of theorems by Halpern-Leistner and Ballard, Favero and Katzarkov. Which they kind of discovered kind of around the same time. By the way, this is only one person with like a hyphenated last name. So it's the following. So again, let's say that X, you have an action, it's a group. Let's say this is a reductive group. This is an algebraic variety. Let's suppose it's smooth. Let's suppose it's projective over affine. But doesn't really, you can forget about that if you want. Now let's say that you choose an ample line bundle. Ample, so let's say that with an action, right? Because you have to linearize it, meaning you have to choose an action of G, sorry. So like of G linearized ample line bundle. So you want to study the GAT quotient that you get with this one. And on the other hand, you also have, so you want to study the GAT quotient that you get when you have chosen this line bundle. And on the other hand, you have the entire X modulo the group. So okay, this the correct way to make sense of this is, let's think of this as a stack. So we want to compare the derived categories of these 2 things. And by this, I mean the derived category of the stack, which means just, objects that are here, but with an action. So you impose like an action on an object in the derived category of X. And here, I mean objects here with an action of G. So let's think of this as stack, even though actually for this one, let's pretend that it's the same as the actual GIT quotient, because there's not much we will lose. And if the action is free, for example, it's the same thing. So but in any way, let's think of this as like an open substack. This is only the semi-stable locus, and this is the entire thing. Let's say that this is like a stack. This is like the GIT. I'm gonna say quotient. I should say like GIT stack, but let's say just the variety that it represents. That it represents it. So every time you have like a coherent sheaf here, you can always restrict it to the open subset. So therefore, you have a functor. Actually, every time you have a chain complex, you can restrict it. So so you have a functor that restricts to this thing. And in principle, this should have way more, objects than this one, because you can restrict, but maybe two things can restrict to the same thing and so on. But the theorem is the following. It tells you exactly how to restrict in order to recover the entire derived category of the GIT quotient, and that's the Windows thing. So the theorem is that so there exists a subcategory of the stack such that when you consider the restriction, then the restriction restricted to this subcategory is actually an equivalence of categories. And that is the window category, this one. This portion of the entire derived category of the entire stack, quotient stack, that restricts to the whole, like equivalently to the whole derived category of the GIT quotient. Yeah, I should say what exactly that is. So but it would involve like a lot of stuff, but let it just be said that it has to do with some weights. You have objects here, and let me say it this way. So this only takes into, this is only a semi-stable locus. So so in order, for example, for a map here to be fully faithful, you need to have some control on the unstable locus, and that's measured by something called weights. So let's say that the window category is like F in so it is the objects that have, I'm gonna like write it really, wrong actually, but I really don't want to like say much about this. So that have some weights in like W plus eta. I'm not going to say what eta is. And yeah, and that's it. And on the unstable locus. Let's just say that it's something that you have to measure on the unstable locus, so that you can make sure that you have some control over the unstable locus, and then on the stable locus, and on the semi-stable locus, and you have what you want. And if this is too abstract, I guess the best example to make is usually Pn. So Pn again is the GIT quotient of an plus 1. So let's write it this way. So an plus 1 minus the origin modulo, multiplicative group. So when you have the entire an plus 1 with the action, then what's the derived category of that? And on the affine space, you only have one bundle, one interesting bundle. But then you can do like a myriad choices for the action, how to linearize it. So you can do a trivial action, or you can choose the action by 1 or by 2 or by n or whatever. Or by -1 or whatever. You actually have here you have like an infinite exceptional collection. And the theorem says that if you restrict to the objects that have like some particular weights, whatever, between W and W plus eta, which in this case happens to be something like, for example, between 0 and n, then that should be enough. So if you restrict to that, then you have, in fact, the derived category of Pn has a full exceptional collection of O all the way to On. And that's the window. So you open the window from here to here. That's your window. It restricts exactly to the derived category of Pn. And there's this mysterious W that I'm putting here. W really is like any number that you want to think of. Well, okay, a tuple of numbers, but in this case, one number. And that means that if you slide the window a little bit, you can still get another window. So you could do from here to here, and that would still work, like from -1 to n-1, like really any, like from k to n plus k, it will still be an exceptional collection of P1. That's the window category. So in fact, this window you can move it. It's not fixed. You can choose it. And more about this theorem. Let me say the following. If you only care about, so there's two things here. This is an equivalence of categories. So that means two things. First of all, it's fully faithful, and it's also essentially surjective, which is actually typically very hard to prove. Like every object here comes from one of the objects here. But if you only care about fully faithfulness, that says that morphisms here and morphisms here are the same. And if you think about that in terms of X or even chief cohomology, it's saying the following. So I won't erase this, but this says that if F is an object here that has whatever condition, like the right weights, which I'm not gonna describe, but it has the right weights, then if you want to compute cohomology here, you will be able to compute it here, because cohomologies are the same, because this is fully faithful. So cohomology on the quotient will be cohomology upstairs, and the cohomology upstairs is just the invariant, the invariant part of the cohomology. And the goal is that, I mean, sometimes this will be much easier to compute, maybe. And also another thing that this says is that if you have a wall, so if L is a wall, so let's say that you have L plus, L minus in either side of the wall. So these are the chambers, and this is what I'm calling L. Then if you take the canonical sheaf on X, and you restrict it to the strictly semi-stable locus, meaning those that are semi-stable but not stable. And if this thing has weights, which again, I'm not really describing, but let's say that this thing has weights that are negative, then you have then the derived category of this quotient will embed in the derived category of this quotient. The derived category of this quotient will embed the derived category of this quotient. And if the weights are 0, then it would be an equivalence of categories. So this kind of partially already answers partially the previous question. So if you have a flip of this type, a GAT flip, where you have like a GAT wall between two chambers like this thing will have these weights, and one of them will embed into the other. And if it's a flop again of this kind, then it's an equivalence of categories. And what this is, the way I like to think about this is like there's a wall here, and you're saying, okay, here this is the entire category, maybe will cross the entire wall. So you're kind of opening a window in the wall, and this crosses to the other side. And even if this does not hold, maybe not the entire category will go all the way. Then you can still, like, some of the objects will satisfy the weights condition. Some objects, those objects will cross through the window across the wall, and those objects, meaning that you can have some subcategory here of the derived category of, you know, whatever X plus, some subcategory of objects that have the correct weights, whatever that means. Maybe here this map will be fully faithful. So these objects, so this entire subcategory will cross the wall, across through the window, and it will appear on the other side as a fully faithful embedding. Maybe not the entire thing, but some part of it. So yeah, and the last few minutes, I still have a couple of minutes, right? Because, well, I mean, it's started a little late. Yeah. Yeah, just let me mention like a few, you know, applications, several, you know, different applications that you can do with this Windows method, with this Windows tool or theory.
So do you find that this is a theorem for these GIT flips?
Yes.
For a general flips, it's just like an idea.
Yeah, it's not, it's a conjecture. Yeah. Dimension 3 is known, but bigger than that. So yeah, for example, if you only care about sheaf cohomology and you don't care about categories at all, this is already pretty good, because it's telling you that cohomologies here can be computed here if you choose the right object. And by the way, here by F, I'm abusing the notation a bit because I mean the restriction of F to this locus. And here, I mean, F in X. In any case, so one application is think back to the example of P1 to the n modulo PGL2, and that depends on how you choose the linearization. If you consider this variety, well, maybe I'll call it Y because I'm calling X the master space, and maybe that. Then it satisfies the following: for every ample line bundle L, you have the following: every power of omega tensor with any ample line bundle has no higher cohomology. You can show that using this. This is a GAT quotient. So how do you show that? Well, this thing you compute it upstairs, meaning on the entire P1 to the n. Well, power of L is no, well, positive power. Any positive power is ample, but it has to be ample. L works, yeah. Yeah. Here, this is really misleading because what is this and P1 to the n? You have to instead of putting this, because this doesn't make sense, what you need to put is like some object here, some object that restricts to that. So you have to find that and then compute cohomology here, which is easier, and show that the invariants are 0. And that's how you show it. And this is a property called like plot vanishing. It's kind of like, besides this and like toric varieties and a few others, it's like hard to find. It's like very restricted and more than that kind of vanishing. It's more than so very few known examples of varieties satisfy this vanishing. So it's like an interesting application already from the point of view of cohomology. If you care about the derived categories, then you can look at the following result, for instance, like this is by Castravet and Favero, that the stack of rational curves with n marked points, the stable rational curves with n marked points, has a full exceptional collection that is invariant under Sn, under the action of Sn. So if you permute the points, the exceptional collection stays the same. And the way you show that is, well, first you have to reduce it to proving it in some tacit spaces. So to some tacit spaces like M P0, something like that, and these spaces are well, this kind of spaces again. Well, I mean, there's way more, but one of the parts of, I mean, I'm oversimplifying, but one of the parts that you have to show is that you have such an exceptional collection here, and once you want to prove an exceptional collection here, then you want to prove that these things, a lot of cohomologies and our forms vanish. you can show it instead of in the quotient, you want to show it here. And that's again where the windows comes in. And if you care about derived categories and how you know, one window makes you cross from one chamber to another, then there's this other theorem. Well, I'm not going to say much about this, but I talked about this last time. So this is myself. Is that you can find so on the if you consider the moduli space of rank 2 bundles on a curve, and you look at the derived category of it, it has a bunch of copies of the derived category of the curve. The symmetric, well, also a point, also symmetric powers of the curve, and all the way to 1. All the way to G minus 1, one copy of this one, and possibly another one that we expect that it should be 0. But the way, maybe more important for this purpose, like what's the method of considering this? Well, instead of considering this moduli space, you consider moduli space of stable pairs, which with some stability condition. If you vary the stability condition, you will have a bunch of those. And this maps to our, let's say that this is n. This maps to our space, and in each of these, there's a wall. There's wall crossing, and the way you embed, for example, this into the derived category of this is first you embed it here. This subcategory, you make it cross the wall through the windows, and you make sure that it will cross every wall through the window, and then all the way to this one. And then there's also like a final argument with this, but for our purposes, the interesting part is that, for example, if D of, I don't know, sim 3 of C, you embed it here, and then it crosses the wall, and it makes it all the way to the other side. And this is how the GAT variation plays out in the setting of windows. So yeah, that's what I wanted to say. Thank you.
Thank you very much. Is there any question?
You told us about what is this P?
Oh yeah, because here, you know, we know that we have embedding of all these blocks, but we don't know like what that will be full. That it will generate the entire derived category. So P is whatever is left, which we suppose it should be 0, but in general, it's like hard to prove that it's exhaustive. It's usually the hardest part to show that this generates everything. We don't know yet, but we expect it should be 0.
Yeah, maybe a naive question. When you design the walls and the chambers, are the lines hyperplane always, or is the case in another one? You have bounded components sometimes, right? Do they have some interpretation because you have bounded and unbounded, or no?
I mean, all of them are unbounded. It's like it's a cone, really. So they are unbounded. I mean, you can like an ample line bundle, you can raise it to whatever power, and you can have like an entire array, so it will be always unbounded. And for the other one, are they always hyperplane? I don't think so. Not necessarily. No, maybe they are, because it's like a very specific, you know, concrete way of saying it's like you have to do like this moment function, and then when the maximum is like bigger than 0. I'm not sure if they are always hyperplanes, but yeah. I was a little loose also with the language, because like an entire hyperplane may consist of like you would consider that like more than one wall. Like if this is like if the picture is like this, you would say like maybe this is a wall, then this is a wall, and this is would be like another wall, like another cell. Cell. I think people will call this a wall, and then each of these would be like a cell. So for example, this quotient would be different from this quotient, and so on. But I mean, the picture is kind of like what you would imagine. More questions?
Okay. Is there any other question? Okay, if not, let's thanks to